So we are beginning our next session on limits, fits, tolerance and gauge design. In previous session, we have discussed some basic terms and definitions related to limit fits. In that, first is whole. So all the internal features are considered as a whole. Shaft, all the external features, they are considered as a shaft. Then basic size. Basic size and nominal size are the required dimension as per the drawings. For example, if we are talking about shaft running in the bearing, then diameter of shaft and diameter of internal race of bearing as per the design, that is called as a basic size. Basic size for two matting part, that is same for shaft external diameter and for bearing internal diameter, that are having same basic size. Actual size is the dimension of component after manufacturing, and always, as we discussed in previous session, always we get some variation in the manufacture dimension due to so many factors are involved during the manufacturing, during the inspection, due to some material variation, and due to those variation always actual size is having some deviation, some change compared to basic size or the design size, and that variation is what we are allowing, that is called as a tolerance. So permissible variation in the actual size of dimension with respect to basic or nominal or design size, that is called as a tolerance. Then zero line is the line drawn which indicating basic size, so that is our reference line. Limits of size means we have given some variation in the dimension. So here you can clearly see in this drawing, this is what the allowable variation in the size of whole feature. Then if manufacturer dimension is with extremely low dimension, that is called as a lower limit or minimum limit, and if you get dimension of manufactured part up to this line, then that is called as a maximum limit or upper limit. So you have allowed variation in this range. So this range, this hedge portion is indicating tolerance. If dimension of manufactured path within this range, then that would be acceptable. Okay, same is indicated in terms of hole and shaft feature. This is what we discussed in previous session. Then this is about indication of basic size and tolerance. So here you can see this is shaft feature, external feature. So external diameter of shaft, that is 40. So that is basic size actually. Plus or minus, we have allow variation plus or minus 0.01. So total variation in dimension is plus 0.01 to minus 0.01. So total tolerance is 0.02, and lower limit would be 40 minus 0.01 and upper limit would be 40 plus 0.01. So here you can see lower limit is 39.99 and upper limit is 40.01. If you take difference between 40.01 and 39.99, means upper limit minus lower limit, then that will give width of this hedge portion, which is called as a tolerance given to component. Then next we are moving further with today's session discussion. So maximum matter limit and least matter limit, abbreviation used for this two is MML, maximum matter limit, and LML, least matter limit. Now to understand this, maximum material limit means when maximum material utilized in manufacturing of any component. Suppose if we take case of hole feature, means external feature, then here you can see this is the hole with diameter 39.99, and this hole, outer hole, that is with diameter 40.01. So actually this is lower limit of hole and this is upper limit of hole. 40.01 is the upper limit of hole and 39.99 is the lower limit of hole. And if you take difference, then you get this annulus ring, which is called as a tolerance of hole feature. So in case of hole feature, if you produce hole with the lower limit 39.99, then this much of hedge portion, that much of material utilized more. And if you produce hole with 40.01, then less material will be utilized. That's why for hole feature or for internal feature, lower limit is called as maximum material limit. So 39.99 is called as a list maximum material limit, and 40.01, then this much of less amount of material is used in manufacturing of hole. So 40.01 upper limit of hole is considered as a list material limit for hole. Now same if we try to understand for shaft feature, means external feature, this is shaft. So similarly here also same tolerance zone, same limits. So lower limit of shaft, that is 39.99, and upper limit of shaft, that is 40.01. If you take a difference, then you get tolerance of plus or minus 0.01, and the absolute tolerance is 0.02 mm, because from basic size upper side we have allowed variation plus 0.01, and with respect to basic side lower side we have allowed tolerance minus 0.01. So overall tolerance is 0.02 mm. Now in case of shaft feature or external feature, if you produce shaft with lower limit, means 39.99, then less amount of material is utilized. That's why for shaft feature or for all the external features, lower limit is considered as a least material limit. But if you produce shaft with 40.01, then this hedge portion is the amount of material utilized more compared to 39.99. So for shaft feature, upper limit is considered as a maximum material limit. So it is very easy to understand now. If if more material is utilized, then that limit is called as a maximum material limit, and less material is utilized, then that limit is called as a uh, um, least material limit. So for external features, lower limit is called for the internal feature, hole feature, lower limit is called as a maximum material limit and upper limit is called as a least material limit. Similarly, for shaft feature, lower limit is called as a least material limit and upper limit is called as a maximum material limit. So I hope you understand. Now we move further. Okay, then how to decide tolerance actually? So here you can see in this table different tolerance grades are indicated. This IT is the designation used for tolerance. It's an abbreviation used for tolerance. So different grades are written here. IT01, IT0 up to IT5. Then these grades are actually indicating the manufacturing process. Which manufacturing process can give you which IT grade? So here if you see IT5, then if you use uh, lapping operation or fine boring or grinding operation, then you get tolerance or the variation in the dimension of grade IT5. We will try to understand this grade later, but just right now uh, consider these grades are actually indicating the tolerance. How to decide tolerance? So tolerance is actually depending on type of manufacturing process. Each and every manufacturing process, they are having their own capability of dimensional accuracy. So here this IT5 is the tolerance grade which can be achieved by lapping, boring and grinding operation. Okay. So standard tolerance, that is IT grade. So these are the different grades, and these are the equation to find out tolerance value actually. So IT5 could be find out by this equation, 0.7 times IT6, and here you can see two columns. These two columns are indicating two different equations actually. IT5 is equals to 0.7 into IT6. This equation will next give you 7 small I, or it can be 7 capital I. Now, if your basic size is below 500 mm or up to 500 mm, then you need to use equation given in this column. If your basic size is in range of 500 to 3150, then you need to use this column equations. So next grades, that is IT6 to up to IT18. So here if you see total how many grades are given as per Indian standards, IT0, 1, 2, IT18. So total 20 grades are there. Total 20 tolerance grades are there, and these grades are actually as per the manufacturing process capability. So if you see here IT7, then IT7 grade can be achieved if you follow turning, broaching and boring operation. And this is fine boring, and here we have coarse boring. So if you follow coarse boring means if you keep high depth of cut, and if you go for high quality turning operation or broaching operation, then you get dimensional variation of grade IT7. So tolerance value of IT7. Now how to find out numeric value of IT7? That is by using this equation, 16 small I or 16 capital I. Again I am repeating, if your basic size is below 500 mm, then you need to use this column equation, 25 times small I. If your basic size is in range of 500 to 3150 mm, then you need to use this column. So as per this column, only change in small I and capital I. What is small I and capital I? That now we'll discuss. But before that, as this table is represented in terms of sketch here. So here you can see, as you move from uh, tolerance grade, lower tolerance grade to higher tolerance grade, means from bottom to up, then 1 to 16 if you move, then on this side, on the vertical axis, you can see that tolerance value is keep on increasing. So this 1, 2, 3, these are nothing but tolerance grades actually, IT1, IT2 up to IT16. So IT16 is sand casting. So if you follow sand casting, then you get tolerance of IT16 grade. And as per IT16 grade, if you see how much tolerance value you are getting, it is close to 2500 micron. Okay, so you can clearly see in this graphical representation, if you move from lower tolerance to higher tolerance value, then your lower tolerance grade to higher tolerance grade value, then your tolerance value is keep on increasing. What is the understanding of tolerance value increasing? Tolerance value increasing means amount of dimension variation is increasing. Amount of dimension variation increasing means possibility of manufacturing error is increasing. So you get tolerance in range up to 20, close to 2500 if you follow sand casting operation. So sand casting operation is the very poor, very poor in case of dimensional accuracy. Clear? So sand casting can give you very less dimensional accuracy. That is what the meaning of this graphical representation. Now next we move further. Now how to find out then those tolerance values actually? How to find out that IT1 value, IT2 value? Then if I move you back to previous slide, then IT6, IT7, this all IT grades, they are actually given in terms of one series. If you look here, this IT6 is equals to 10 times small I into 1.6 raised to 0. Now if you move to IT7, then 10 times I into 1.6 raised to 1. Now this power is keep on increasing by step 1. If you go to IT8, then compared to IT7, equation is 10I remains constant in this series, but multiplier of that is 1.6 raised to now power 2. If you go to IT9, then 1.6 raised to power 3. So power of 1.6, that is increasing in each step by 1. And if you simplify this equation, first of all, suppose IT7, then 10 times I into 1.6 raised to 1. Then 1.6 raised to 1 is 1.6 into 10, then you get 16 times small I. If you go to 1.6, then you 1.6 raised to 2, then you get 2.5, and 2.5 multiplied to 10, then you get 25. 25 into I, so you get 25 times small I as a IT8 equation. So IT8 can be achieved by center lid turning, boring, reaming. These are the manufacturing process which can give you dimensional accuracy of IT8 level. Okay, now next we try to understand how to find then small I. If you are able to find out small I for IT8, then multiply that small I with 25, then that will give you tolerance value. So in this slide we see one new equation, because this I is called as a standard tolerance factor. Now standard tolerance factor, if you just look in previous slide, then up to 500 mm basic size small I is used, and in the range of 500 to 150 mm capital I is used as a tolerance factor. So both are having different equations. Small I equation is 0.45 times cube root of capital D plus 0.001 times capital D. Okay, so this is equation of small I. Now to solve this small I, we should find out capital D. Then what is capital D? If you look here, capital D is equals to square root of product between D1 and D2. Now what is D1 and D2? That is next question. So here you can see this table. This table is actually indicating some size, step size. This step size is for basic size. As you know now, what is basic size? Basic size is the design dimension of your mechanical component. So if you look here, two different step size series are indicated. This is called as a general case and this is called as a special case. First, just see this general case. Then as per general case, if your basic size is in range of 3 to 6, means if your basic size is 5 mm, then 5 mm is 10 in range of 3 to 6, then D1, here this D1 is 3 and D2 is 6. Then 3 into 6, 18, square root of 18, that is your capital D. Now after finding capital D, put that capital D in equation of tolerance factor small I, then you get some numeric value of small I. Now this small I you need to use in this tolerance table equation, tolerance grade equation. Now 25 times into I, then that will give you value of IT8 grade. I hope this process is clear. Similarly, now if you take suppose basic size 60 mm, so 60 mm basic size, that is in range of 50 to 80 as per the general cases. Then 50 to 80, then D1 is 50, D2 is 80. Now D1 is 50 into 80, find out this small this capital D, put capital D in this equation of small I, then you will get numeric value of small I. Then put this numeric value of small I in the tolerance grade equation, then that will give you numeric value of tolerance. Okay, now here one thing is very much important: unit conversion. What is unit conversion? If you look here, if you look this table, then unit of this 18 and 30, that is in mm, millimeters. So your basic size, if I am telling you basic size is 60, then it is 60 mm. So 60 mm is in range of 50 mm to 80 mm. Okay, so 50 mm to 80 mm you put here, then you get capital D value, so that is in mm. Now as you use this equation of tolerance factor small I, then put this capital D in mm, and if you solve that equation, then whatever the numeric value you are getting, that is having unit micron. Please remember this. If you are solving capital D1, you are solving capital D by taking capital D1 and capital D2 in mm, then you get numeric value of capital D in mm. Now you need to put D in mm in equation of tolerance factor small I, and after solving it, whatever the numeric value you are getting, that is in micron, because by default this 0.001D, that is by default conversion of mm unit into micron unit. Okay, so this is very important uh, thing which you need to remember. Now again, that same table, if you look here, this same table, but here entire series is given and type of manufacturing process is also listed, which can give you type of tolerance grade. Same is summarized in this small table. Okay, so if you look here, IT5 to IT16 grades, then different equations are given. 7 times tolerance index I, 10 times, if you take IT6, then 10 times I, so that I is tolerance factor. How to find tolerance factor, that is what we discussed. Okay, so I hope it is clear how to find out tolerance values for this problem. Okay, now next is representation of tolerance value. Representation of tolerance value in system of writing tolerance in drawings. So two ways are there, unilateral and bilateral. So if you look here, system of writing tolerance, so two ways are there to write tolerance. One is a unilateral and second is bilateral. Now let us try to understand this unilateral and bilateral using this table. If you look this table, then here tolerance method, limit dimension means this is upper limit, 9 mm is the upper limit and 8.5 mm is the lower limit. So same is written here, dimension in terms of limits. So upper limit 9 mm is upper limit, 8.50 is the lower limit. Now here what is done, I have kept here limits constant, upper limit and lower limit kept here as a constant. And now let us differentiate, or let us try to understand what is the unilateral system and bilateral system. So if you look here, equal bilateral system and unequal bilateral system. What is meaning of bilateral? See, bilateral means if you keep your tolerance zone such that it is split on both the sides of basic size. Let us try to understand this with one graphical representation. Suppose this is my shaft, external feature. Let me also give you front view of this. Then this is front view. Diameter of shaft is visible here, and this is side view. Now suppose if I give the tolerance zone, suppose sorry, let me paste this. Okay, suppose this circle is representing maximum material limit, means upper limit of shaft, and this violet color circle that representing lower limit or the least material limit of shaft in front view. Now in side view, if I indicate, if I take difference between this upper limit and lower limit of shaft, then I get this portion as my tolerance zone. Okay, so same tolerance zone I am indicating here in side view. Then suppose, okay, so if I produce shaft with this magenta, this violet color, then shaft with the lower limit. If I produce shaft with this green color, then that is shaft with the upper limit. And this is what the distance between this green line and violet line, that is called as a tolerance zone, acceptable dimension. So if by chance shaft is produced below this violet circle, means below lower limit, then that shaft is considered as an undersize, that would not be accepted. If shaft is produced with the diameter more than the upper limit, means more than this green color, then shaft is called as an oversize, again it is not accepted. Only shaft would be accepted if dimension of shaft is in the range of this green line to this violet line. Yeah, so that is what the understanding of tolerance. So tolerance is acceptable range. So this line, these two lines, this zone is indicating, let me show you zone. So this zone, this yellow color zone with this yellow color, that is nothing but the tolerance zone. So if dimension within this yellow color, then that would be accepted. Okay, now let me show you basic size. For example, basic size is 25 mm. If now let me show you basic size line. Suppose if this is the basic size line, then what you see here, suppose this blue color line is the basic size. Suppose for example basic size is 25 mm. As per my design drawing, I want diameter of shaft is 25 mm. The 25 mm is called as the basic size. So this blue line stands for 25 mm line. So this height, let me show you height. Then this height is called as a, from the lowest line, this height is called as a basic size. Okay, so if I consider tolerance zone, this yellow tolerance zone is split on both the sides of basic size, then that is what called as a bilateral tolerance. That is called as a bilateral tolerance. Okay, and if just consider one another line with orange color, if you consider one another line, this orange line, then with respect to this orange line is, suppose you have, if you assume as a basic size line, then look here, this entire yellow color tolerance zone that is above orange line, then if you give that type of tolerancing, then that is called as a unilateral tolerancing. That is called as a unilateral tolerance. That is called as a unilateral tolerance. Okay, so I think this graphical representation is clear to all. Now let us try to understand this. So equal bilateral tolerance means, if you consider this blue line as a basic size, and if you put your tolerance zone, this yellow tolerance zone, says that it is equally split on the both the sides, means your basic size is exactly, this basic size line is exactly passing through center of this yellow zone, your tolerance zone, then that is called as a equal bilateral tolerance dimension. Then here you can see, suppose 8.75 is the basic size, and if you give plus 0.025 mm variation above it and minus 0.025 mm below it, then equally split about 8.75, 0.25 mm dimension is equally split about 8.75 mm basic size. Clear? Then that is called as a equal bilateral. Now let us try to find out limits. Then 8.75 plus 0.25, then 9 mm is the upper limit. 8.75 minus 0.25, then 8.50 is called as a lower limit. So 0.25 is equally split on both the sides. Okay, similarly now unequal bilateral. Bilateral is there, means this blue line
is splitting entire tolerance zone, this yellow tolerance zone. But now blue line is not exactly passing through the center of this tolerance zone, yellow tolerance zone. It is splitting yellow tolerance zone but not equal, unequal. Then that is called as an unequal bilateral tolerance. So here you can see, suppose now our basic size is changed because location of this uh, blue line is changed, basic size line is changed. Now that is suppose 8.8. So 8.8 is a basic size. Now how much variation I am allowing above basic size here? Plus 0.2. So I am giving variation of plus 0.2. But how much variation I am allowing below basic size? Minus 0.3. So now variation above and below basic size is not same, because 8.8 is your basic size. You are giving positive variation 0.2 and negative variation 0.3. Here in this above case we are giving variation same on both the side, plus 0.25 and minus 0.25. That's why that called as a equal. But here that is unequal. On positive side less dimension variation, on negative side more dimension variation. On positive side 0.2 and on negative side 0.3. Then that type of tolerancing is called as an unequal bilateral tolerance dimension. So now if you try to find out limits, then 8.8 plus 0.2, so 9 mm is the upper limit. 8.8 minus 0.3, that gives us 8.50, which is lower limit. Okay, so this is about if you consider blue line as your basic size line. But now next is about unilateral system. So when we call as a unilateral system, if you consider this orange line as your basic size line, then entire tolerance zone is above basic size line. Now let me remove this blue line. So if you have this type of system, then this is what called as your basic size. Actually this yellow line, this orange line is called as your basic size, and now entire yellow tolerance zone of shaft that is above basic size. So that's why it is called as a unilateral, because the entire tolerance zone is above basic size. Okay, so unilateral tolerance system, but positive and negative, two possibilities are there. Here this graphical representation is giving us positive tolerancing because entire tolerance zone is above basic size. So that is called as a positive tolerance. If entire yellow zone, if you consider below orange line, basic size line, then that would be called as a negative unilateral tolerancing. Okay, now let us try to understand. This is positive, so basic size is considered as 8.5. So 8.5, above limit is plus 0.5 and 0. So let me relocate basic size line as per the given dimension. So here see 8.5 is the basic size. So lower limit is 0. So 8.5 plus 0, then 8.5 itself is the lower limit as well as basic size, and 8.5 plus 0.5, then 9 mm is the upper limit. So 8.5 is the lower limit, 9 mm is upper limit. But now basic size is also 8.5 and lower limit is also 8.5. So in this representation, this violet line is indicating 8.5 and this green line is indicating 9 mm. And now if I draw basic size line, orange color line, then the basic size is overlapping on this lower limit of shaft. Now I hope it is clear to all, because now here also your tolerance zone of shaft that is above basic size. Okay, now 8.5 plus 0.5, so 9 mm. So this line is 9 mm line, this green line, and 8.5 plus 0, then 8.5 is the lower limit. So this violet color line or this yellow color line, this orange line, means the basic size is directly equals to lower limit of shaft. Now let us try to understand this unilateral tolerance dimension, but negative. Means here if you see, when you let me again relocate basic size line as per the given condition. So here if tolerance zone is entirely below basic size, then that is called as a unilateral but negative. Now first of all, let us try to find out limits. So 9, 0 to minus 0.5. So upper limit of shaft now 9 plus 0. So 9 is the upper limit and 9 minus 0.5. Then 8.5 is the lower limit of shaft. Now here if you see, 9 is the upper limit of shaft and 9 is the basic size also. So if I draw basic size line, then basic size line is passing through upper limit of shaft. So that overlap on this green color line. So if you see, this is basic size, then entire yellow tolerance zone is below basic size. That's why it is called as a negative unilateral tolerance. So now I hope you understand what is unilateral and what is bilateral. Now let us move further. Okay, now one another important term is deviation. Now what is meaning of deviation? As per the definition, deviation is algebraic difference between actual size and basic size. Okay, now actual size is the size which you get after manufacturing, as we discussed in previous session, and basic size is the size which is as per the design dimension, which is actually V watt. Okay, that is called as a basic size. So that is, I think, clear. Now as per deviation, it is difference between actual size and basic size. So here two possibilities of actual size. It could be in range of if you just try to understand this graphical representation, then here this line stands for 0 line. So 0 line is indicating basic size line. Okay, and this rectangle stands for tolerance zone. So if you remember our IT grade equation, those IT grade equation, they were giving you numeric value. Okay, we just discuss up to this in this session to make this session short. In next session, we'll try to understand, or we'll just solve one problem to find out tolerance value numerically, and then after we'll discuss this deviation, so that will give you more better understanding. So we keep up to this. In next video, in next session, we'll move further.